Okay, guys. Hopefully you were able to complete the gizmo from Explore Learning that looked at the law of reflection, and you found that the angle of incidence should be equal to the angle of reflection. So that's the angle that the incoming ray presents with respect to the normal. So with respect to that 90 degree from the mirror is the same as the angle of the outgoing ray after it reflects off the mirror. So now we're going to look at something called refraction. So we know what reflection is. Refraction might be a slightly different concept, but you've certainly experienced it anytime you look into the water, when you realize that, when you try to pick something up under the water, it's in a slightly different place than you'd expect. And that's because of this property called refraction. So let's take a look. And as you'll see there, um, the subtitle is Why Light Changes Direction When It Enters a New Medium. So let's examine that. So light, if you recall from last week, is a bit strange because it's both a wave and a particle. So they called that wave-particle duality. And it's something that most other things like sound travels in waves, but it's not a particle. So that's why, of course, you don't hear sound if you're in outer space, whereas light is able to travel through because particles can travel, most waves cannot. Um, no waves can other than light. So light, for all intents and purposes, will travel in a straight line at the speed of light, which is 300,000 kilometers per second. Now, when light changes medium, and by medium here, I just mean the substance through which the light is passing. So right now, for example, the light that, well, I've got some lights on in this room, but the light from the sun is coming in and it's traveled through space. It's then traveled through our atmosphere. It travels through my window. It travels through the air in this room. It travels through the lenses in my glasses, travels through the air in between those two, and then it enters my eye. So it actually changes medium or media very, that was 4 or 5 changes before it actually reaches my eye. And even once it hits my eye, it changes medium yet again and again and again until that image is produced on my retina, which we'll learn. That'll be the last thing we learn when we look at physiology of the eye. So it bends slightly. And the way in which it bends depends on the densities of the medium that it's coming from and the density of the medium that it's entering. So yeah, looks like I just went through all that. So let's continue. So in space, as I said, space is a vacuum. So there's no air there. Most things that travel in waves would not be allowed to travel through space unless they are consisting of particles, which, as I said, that's special to light because of that wave particle duality. Now, when light travels, for example, from space through and it hits our atmosphere. So our atmosphere, of course, is where we're all in right now, and it consists mostly of nitrogen, about 78% nitrogen, 21% oxygen, some other trace gases, carbon dioxide, etc. And when light travels from that vacuum of space into the atmosphere, where there's now particles of air, it's going to slow down. But wait a second, you said, Mr. Sanford, that light travels at the speed of light. Well, that's true. So it's an apparent slowdown. Each individual photon, remember how we discussed photons being produced when an atom receives some energy, becomes excited, an electron will jump to a higher energy level or shell. It's unstable so that it can't stay there for long. When it comes back down, it releases that energy that it had in the form of a photon. And these photons travel at the speed of light. However, when light goes from something like the vacuum of space to the atmosphere, or from the air through my glass lenses in my glasses, what happens is the individual photons will bounce around because it's gone from something with, nothing, the vacuum of space, into hitting all these air particles. So it bounces around in between them. And when it does that, the apparent speed, so the time it takes for it to go from here to here, is longer in a denser medium because it's actually bouncing off particles. So it appears as though it slows down, but it doesn't really slow down. That photon, as it bounces, is still traveling at the speed of light, but for it to travel a certain distance, it will take a bit longer because of that bouncing around off of those particles, being absorbed and re-emitted, absorbed and re-emitted. So, for example, certain types of glass, rather than the 300,000 kilometers per second that light travels in space, in the vacuum of space, it can slow down to 200,000 kilometers per second if it's going through thick glass. And these are actually properties that are used by opticians. If you saw the video, the Cosmos video that I posted last week, they talked about the creation of optical grade glass and lenses. That's what allows me to see. They've perfected it so that they can get the exact density and shape curvature of these lenses so that it bends those light rays sufficiently that it focuses images directly on my retina so I can see quite well with my glasses on and quite terribly with my glasses off. Yeah, let's put those back on. Okay. So we know that the hardest mineral that we know of is diamond, and that can take light that was traveling at 300,000 kilometers per second from the sun, slow down slightly by our atmosphere, and it can slow it down to as little as 125,000 kilometers per second. And this is also one of the properties that uh, jewelers will use. They'll shape a diamond in a certain way and know that light will bend in a certain way when it hits that diamond so that it produces something called total internal reflection. So light rays will enter, keep bouncing, 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 and cause the diamond to shine really brightly, which is something people like, I guess. All right. Now, when light leaves this denser medium, like my lenses and my glasses, and then comes back to that space of air before it hits my eye, all of a sudden it speeds back up. And that would be impossible if that light truly actually slowed down because there's nothing propelling it. That would violate one of Newton's fundamental laws. You can't just pick up speed unless there's a force pushing you. And if since there is no force, it wouldn't make sense, except that, recall I said that it doesn't actually truly slow down. It's just that bouncing when it enters a denser medium, bouncing between particles, hitting something, being absorbed, re-emitted. So the apparent speed is slower. So when all of a sudden it enters a medium that's not as dense, it can now freely travel at the true speed, which is 300,000 kilometers per second, or maybe slightly less if there is still, if it's not a complete vacuum. Right. So light does slow down a bit in air, but it's not a huge effect. So even though we obviously have particles of air here that the light, once it reaches from that vacuum of space, is able to bounce off of, be absorbed and re-emitted, the apparent slowdown isn't nearly as much as when light hits glass or when light hits water or when light certainly hits diamond. So we can't really tell that much. And in fact, if you look at the speed of light, I rounded it off for you guys. It's really 299,792 kilometers per second, not 300,000. My apologies for being imprecise. If we look at that speed of light in air, it's pretty similar. So 299,703 kilometers per second versus 299,792 kilometers per second. Very, 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 very fast. Either way, you would certainly not be able to notice much of a difference. So, because of this apparent slowdown, how does that affect the direction that that light ray travels? Well, let's take a look. So, when a light ray hits a new medium, so it's going from air into water or air into glass, it's going to actually bend. And the direction in which it bends depends on the densities of those two mediums that it's going through. So if you were to draw a diagram, so hopefully you saw in that gizmo that we did, that when we look at ray diagrams, and ray diagrams are just a way to show what's happening to light rays as they either reflect off a surface like a mirror or perhaps refract if they're going through something that's transparent or translucent. We can see that if you were to draw that normal, and a normal is just a line perpendicular to the surface of a mirror or a lens or water or whatever it is, when light goes from something less dense, for example, air, into something more dense, for example, water, that light ray is going to bend towards the normal. And if we, so air to glass or air to water, if we're to take a look at what that looks like in a diagram, on the top, I've got air, so a light ray is going to be coming from the air, and it's going to hit glass, just like the lens in my glasses. And we call that incoming ray an incident ray. That line that you see there at 90 degrees, right here, this is the normal. And I just said that since glass is more dense than air, that light ray that travels through the glass from the air is going to bend towards the normal. So instead of continuing on the path, like you might expect, rather, it's going to bend towards that normal. Here's the normal, here's the expected path of that light ray, and because it goes from something less dense like air into something more dense like glass, it will bend towards the normal. Now, the degree to which it bends depends on the difference in the density of those two media. So glass, there are many types of glass. If this was a particularly dense type of glass, it might bend more. It would bend more towards the normal. If it was something like diamond, it would bend severely towards that normal. And now we have that refracted ray. So the incoming ray is called the incident ray. The ray that passes through and bends is called the refracted ray. Now, what happens then? I told you there's an apparent speed up of that light or acceleration of that light as it goes from something that is something that is more dense into something that is less dense. And again, that wouldn't be possible if that light truly slowed down, but remember, it doesn't, right? It's just bouncing around, each photon traveling at the speed of light. So if we look at that reverse case, so going from maybe glass to air, like it does after it passes through my lens and then into that pocket of air before it reaches my eye, or from water to air, what you're going to have is the opposite occurring with respect to that particular light ray. So you're going to have, that's my wife in the background running to the door. You're going to have that light ray bend away from the normal. So let's take a look at how that appears if I were to draw that same ray diagram that you saw, but the case being reversed. So here we have glass on the top now. So this is light going through glass and then emerging from the glass back to the air. So we see again, remember that incoming ray is called the incident ray. And here it is going through glass, just like the lenses in my glasses. And I'll draw the normal again. Remember, the normal is 90 degrees or perpendicular to those two surfaces. And again, if it were the same medium, you would expect that light ray to continue along its path. However, since of course it is changing from glass to air, something more dense to something less dense, we see a bending or refracting of that ray away from the normal. And again, the degree to which that bends or refracts will depend on the differences in the densities of those two substances. The greater the difference, the more that light ray bends. And in this case, so if it was something super dense, like perhaps diamond on the top, it would bend severely away from that normal. So there it is, that refracted ray bending away from the normal. So that happens, if you can imagine, it's tough to imagine since we're dealing with photons that are minuscule, tiny in size. But if you imagine that light wave hitting the surface at an angle, part of that wave hits the surface before the rest of it does. And I imagine this similar to if you've ever had a shopping cart and maybe you're shopping at Loblaws or something like that, a place where they've got a clothing section. And most of the grocery store is kind of slick tile. But then in the clothing section, you've got carpet. Well, if you were pushing your cart on an angle, and let's pretend it's a cart that actually goes straight. The wheels aren't messed up like most of them. But if you're pushing that cart on an angle from the tile, moving towards that carpet, part of that shopping cart is going to hit the carpet first. So both wheels don't hit at the same time when you're moving on an angle. One wheel will hit first. And because of that change, you're going to get a slowdown from the fast tile to the slow carpet. Since part of it hits first, that part is going to catch, slow the cart down, and you're going to get a bending, a turn of that cart. And that's similar to what happens with light. Of course, again, it's harder to imagine because photons are so tiny, but part of that light ray will hit that boundary, that border between the two mediums first, and that will cause that bend or refraction of those light rays. And you can kind of see it there, though for some reason that looks a little granular. I'm not sure why that's so pixelated, but that's okay. You can see the direction to which this arrow is going. If this is the faster medium, so this is air, this is the slower medium, that's glass or water. You can kind of tell my shopping cart analogy there. I'm pushing the cart on tile, tile, tile. Oh, I hit this boundary. This part that I'm highlighting here hits first, and since it's slower, it catches and causes the cart to bend away from the trajectory that you would expect if it was entirely tile. So because of that, it will bend it going from this fast medium to a slower medium. You get a bending towards the normal. And again, that the reason this is so important, these properties of refraction are the way in which lenses, be they in my glasses or in a microscope or in a telescope, that's how they work. We've been able to figure out exact densities and curvatures so that we can focus images like we did in biology using a microscope to see at the cellular level or subcellular level, or more importantly for me, being able to take what is my terrible vision, because since I'm nearsighted and anyone else that's nearsighted probably has eyeballs that are shaped in such a way that those light rays don't bend and meet to focus an image clearly on the retina. So what we do, or not we, but what opticians have done, is be able to get exact curvatures of these lenses and exact densities to bend those light rays just enough, refract those light rays just enough so that by the time they hit my eyeball, they go through my cornea and my lens and eventually hit my retina. They converge perfectly so that with my glasses on, I now can see 20/20. I have perfect vision, whereas with them off, whew, not close. Okay, so I'm going to give you guys a few questions on refraction to work on. And then the final thing that we'll do for this school year, yeah, that's it, is a look at physiology of the eye. Okay, that's all for me today.